Let me introduce quickly the team here from Accenture. On the first side, Ishmael Greval, he is one of our software engineers and the father what we will see later onwards in the demo and in the slides. And my colleague, Teresa Tang, she is one of our managing directors in the tech labs of Accenture and leads there the software and platforms group. And myself, Jürgen Weichenberger, I am one of Accenture's lead data scientists responsible for resources industries, which is sponsoring the examples we will see in the talk. Our talk today is about how to manage models on large scales in the cloud and in parallel on the edge. So there is the demand of running models in the cloud, which we do for 10, 15 years. But now as we have the issue of moving data, because it gets very costly, we also want to run seamless models on the edge and interact with them. And for this reason, we have thought over the past 12 months how we can do that on scale, and especially also in a very efficient and dynamic way. So let's start with an example. Oops, I'm too far. So digital corrosion management is an industry problem around the world. Everything which is made of steel corrodes and falls apart. And therefore, we need a solution. And obviously, it has to be a predictive solution because we need to know where it's corroding. And that leads then to a dynamic process. So it's not static because it changes, environment changes. As you can see then here in this little pipeline, we build a model, we design, we scale, we run, we get feedback, we redesign, we redeploy. So we continuously improve our models and make it work. On the right side, you see then a little bit of examples. What's the outcome? So all these things here run in the cloud, thousands of models at pace and at scale, which we continuously update. Hereby, we are using then complex accurate functions, deep learning, combinations of image learning, computer vision with machine learning, AI, literally all sorts of fun things you can imagine. But the point is, it's not enough, because some of these locations where we need to find corrosion, they're on the edge. And there are, in areas, subsea, for example, I have platforms in the North Sea, the pipes running underground on the seafloor to the land, which I cannot reach. So we need edge models. And that brings us to the next version. Instead of running it in the cloud, we are using drones combined with edge computing to detect where we want and where we need the models. And we don't need to wait before the data is back. I can take a decision on site and make it happen. And therefore, we needed a complete new way of model management, because the edge has not the capability to handle that. So we needed dynamic models which assure that what I'm doing at the edge is continuously accurate. Because if I take a decision out there, the engineer will do something. If he does the wrong thing, he can create millions of dollars of damage. So that is an extremely important element, that you know whenever you do something, it is correct. And the third use case we are using here in this demo is a more classical use case in the way you want to build a model pipeline which is inherently dependent for predictive asset maintenance. And as you can see here, we are running that with thousands of sensors at an extreme high pace. We are running, in this case, 5,500 models. I think more, actually it's already 10,000 models, and it scales up further. And we're running them every 12 seconds. And you have to assure every 12 seconds what you're doing is correct. And if you stop a plant for half an hour, it costs you up to $15 million. And to make that work, it is just not people business anymore. So 5,500 people, our models cannot be managed by 2 people. It needs an army of people, obviously, which is no longer affordable. And to make that really happen, now Ish will show you a little demo, and afterwards how that really works. So Ish, please.
Thanks, Jürgen. Let's move into the demo really quick. So I'm Ish, and I work on the Accenture Labs team as a developer. So using all these use cases, we came up with a strategy on how we should solve this problem. And the prototype that I built, I'll show that really quickly. Okay, so we're going to approach this demo with 3 different personas that we have. So first one being a data scientist, someone like Jürgen who has that domain expertise and knows the use cases inside and out. Someone like me who is a developer, or you can call them an operational engineer. They know where the data is located, how to configure the data pipelines, the IT pipelines properly. And then finally, someone like Teresa who can be a data science manager or the final consumer of the analytics and take that business decision that needs to be done. So in this first screen, what we're looking at is the model catalog, what we call the model catalog. This is a centralized repository for all the models that will be developed for the analytics by someone like Jürgen or Jürgen's team. The core data science goes in here. So in this model catalog, we can see that there are multiple different owners, multiple versions of the models available across several categories in this case. And the key thing to note is that we also have multiple different runtimes available. So this framework supports currently R and Python, but it's very extensible, and we are working on SAS and TensorFlow and Spark as well. So we'll look at an architecture diagram later where it'll make more sense why these runtimes are important. And so in this model catalog, we can see that we have all these models. So let's step into one of them and look at it in detail. So initially, we can see that in this asset performance model, we have some metadata information available, some sort of description, which can be a very robust wiki as well, which describes how the model needs to be used, what is its intent, what's purpose, the data schema that it expects, and the output it will produce. And then we can look at the final components that have been onboarded onto the framework. So in this approach, we let the data scientists do kind of whatever they want in their data science playground, as we call it. So they can choose any kind of tools out there to do the actual building, the validation, the training, the scoring, and the actual building of the model. There are tools out there like Data Robot, RStudio, Python, Jupyter Notebooks, things like that. So once they build the model, they end up with a model binary at the end, which is the final set of weights and the actual algorithm that defines this actual model. So we ask that they onboard that onto the framework along with 3 other things. The first thing is the prediction recipe. So the prediction recipe is supposed to templatize this model. So the data scientist knows what went into the binary, but someone like me can use the prediction recipe to simply just run that model binary, connect it to the different data sources, and configure the model appropriately. Then we also ask the data scientists to provide sort of an evaluation function, since they're the ones who know how this model performs over time and when to capture its drift. They need to give us some sort of an idea of how we capture this evaluation, or how do we evaluate the model so we can know that it has been drifting. And they can either write their own custom parameters or custom functions for this step, or they can choose something out of the box, such as coefficient or Gini coefficients, AUC, ROC curves, things like that, confusion matrix as well. And then finally, we also ask them to provide us some sort of retrain code or retrain functionality, because assuming that the model binary has been created and everything is working properly, when we do capture that the model drifted, we need to be able to take certain actions. The most basic action is stop the model from running everywhere and send the data scientist a notification and email and be like, hey, please update this. But if they did it properly, if they configured all the things properly and they created the model properly, they can provide us the retrain code. So if the data scientist is no longer in the company or in the firm, then they can take that retrain code and retrain the model and then deploy that back into production, going through all the validation steps as well. So that's where it comes, the lifecycle part comes in. So this demo UI is mostly to tell the story, but at the bottom, the tool is a set of APIs. So in this particular lifecycle, we have a very simple one. It's in draft status and then goes into pending approval, and then it becomes active. Because the tool is a set of APIs, the pending approval step could be as simple as Teresa just saying, Jürgen, good job, I'm going to approve this. Or it could be integrated into a very robust existing business process, which might be necessary, especially in financial industries where regulation and auditing is very important. And then we also have the final set of KPIs and parameters that go along with this model, so that this model now, with all this information, becomes sort of a black box, and the data scientist can step away and start working on the next project, while this model becomes self-contained and can be used by someone like me who's an operational engineer. So how do we use this? So let's step to the next part. This is what we call the pipeline catalog. This is where all the configured versions of that model are stored. So the screen Jürgen was showing with the use case earlier, that was for the asset performance model. So let's look at an example of what that looks like. So the temperature and the flow models in this case were created by someone from the surveillance analytics team. They are the domain experts who know how to predict what temperature will look like or flow will look like for that particular asset in the future. And then the asset model was created by someone who is more of a device expert, so to say, the person who knows what that pump is supposed to be able to do, and they know it inside and out. They know when to do maintenance on it. So someone like me, an operational engineer, can then take these models. I don't necessarily know what's going on inside them, but I know the evaluation conditions. I know that it's going to be regulated by the framework, and I can configure them with the actual data sources. So in this case, temperature data coming from some sensor, flow data coming from sensor, and then store it in an asset output. So with this kind of model or this kind of template, we can create a further pipeline template where now this can be taken and deployed on those 5,500 multiple different pumps that we're running in that particular use case. So by black boxing this approach and making it very configurable and modular, it enabled us to take the model that was developed by the data scientist once, and as long as it doesn't drift and as long as it's working properly, we can deploy it at scale in the production environment. We also have another capability available, which is the champion challenger functionality. So if we look at one of those, we can see that in this particular case, the 3 different models are running in parallel through the same data set, and we can create an evaluation function, a custom evaluation function to decide which one is the best and only choose that particular output. And if we do an example of this, then we can see, and we try to make it so that from the model catalog view to the pipeline catalog view, all the way to what we call the instances view, everything is still templatized and is still sort of a generic template that can be run. And every step of the way you make it more and more specific. So in this particular case, when I'm running it, I will provide some sort of sales data so that I can forecast what the sales will look like in the future. And I run it through 3 different models, the RF, ERT, and GBT, and then evaluate them. So once we start this configuration for one particular SKU value, we can see that now we're at the instances screen. So this instance is the final configured run of that particular pipeline. This could be where all the different pumps, the sensors, all of them come together, and we store every single bit of information on what the input data was, what configured parameters were, and what kind of output was generated. So we can see that we actually completed this demand forecast competition. So we can see the input available was that sales file, then the evaluation results. So for that particular SKU value, we had 3 different models that created this error, and then the chosen one was with the least error as well, or the 62. And then the output generated could have gone to some sort of database, but in this case, I just show it on the screen so that we can talk about it and tell the story. So this view would be more like someone like Teresa, who is the final consumer of this analytics and can just look at this. She doesn't need to know how the model was created, how the pipeline was constructed. She can look at this final piece of information and take that business decision that needs to be done. Okay, so let's step back to the slides. Okay, so let's talk about how this overall approach came into play. So as I was talking about, we had the data science playground on the left-hand side, and then once the data scientist creates that particular model and that model binary in the final asset, then we bring it on to the framework where we are able to support multiple different runtimes. We have onboarding and validation built in so that the governance process flows appropriately. We store it into the model library, and then we can create those model pipelines. Those model pipelines become part of this template library, which can be reused across even different configurations or different parameters or different industries, sorry. And then the governance and audit is built on top. As I said, the framework is built as an API, so it is very extensible into just using webhooks to bring it in as with existing business processes or workflows as well. So once we take over the operations, now the model can be continuously running in the production environment. We can deploy it manually, or we can schedule it based on whatever the IT pipeline requires, and then run those monitoring and diagnostic information. So now that every model has that evaluation condition or function available, we can know when it's drifting, and we can capture that health over time as well. And then once we look at the API and then the job server, we can see that Currently the tool that is in production supports R, Python, and SAS and TensorFlow upcoming, but the job server is really where the model runs in itself at the end. So that's a good segue into the architecture slide. So at the top, we see that we have the multiple different kinds of users who will be consuming this application. We have either a custom user interface or just through the APIs, batch tools, things like that. And then the core of the model manager is the set of APIs, the monitoring service, the governance and auditing features, the scheduler, and then the model metadata store. So the metadata store is the key piece of information that brings in everything together. So it's that centralized repository. So all of your models or pipelines or information aren't scattered across different computers on different data scientists. And then at the bottom layer, we see that we have those job servers that execute these models when they need to be executed on particular different runtimes. So one thing that we try to stay away from is the ETL process. So the data that needs to be able to provide it to these models to run, that's separate. So that's why it's grayed out in the box on the left. So the ETL process is we can take the current existing ETL process and just consume the final information for that model to run the analytics on. The development workflow sort of works like this. Again, just a more specific version of the last slide where we have the data scientist development environment. They can choose any kind of tool they want. And once they check in that model, so this is where the whole DevOps thing starts to make sense. It sounds a lot like checking code and validating code and testing and then continuously deploying it. The code then goes in, or the model goes into the centralized catalog and where we can create the pipelines from it and then connect it to the data sets and execute them. So the execution part in the bottom here, you'll see that it has this circle of evaluation and then retrain available. So this is that self-healing and monitoring that we want to continuously be able to run these analytics without breaking any pipelines because of some small error in this example. And then once the evaluation continues to pass, we can keep storing the output and have that whole granular tracking and audit logging available as well. So a few examples that we did with this particular framework, some POCs that we created was, in this case, we had, there are two different kinds of models running. So taking client data, we had some SAS models that were making predictions on finance and risk portfolios, and they would create some scores. And then the evaluation function, for that evaluation part, in this case, the client was using Excel files, and they would load all that data into an Excel file and do some manual inputs and then run it. And they had to do that every single time this model ran. So what we were able to do is, using the existing SAS and Python or our job servers, we created this sort of model pipeline, and now every time that model is executed, and so in this, on the left-hand side, we can see there's the client data part. So once the client data, maybe a table is updated, we can run the entire pipeline. We can have that hooker scheduled. And then every time the model is updated, we run the evaluation script automatically to see how that model had been performing. And we store all of that information back in the model manager database, which can be queried again through an API or this custom UI that I created. The other use case was a deep learning example. So in this case, the top part, the data scientists, some of our data scientist teams in Japan created a model a deep learning model to identify in an image a vehicle, a pedestrian, or some other information as well. So we took that model, that's sort of what their data science playground was. We took that model and then created this model pipeline where we can reuse components such as frame extraction. Now, frame extraction doesn't have to be specific to this particular model. It can be any kind of pipeline can do that, or any kind of input video can do that. And then object localization and object classification then consume this model binary and create the actual output. And so we can create this model pipeline, again, another template, and then deploy it on that particular instance of that input video or any other input video coming from multiple different videos or camera sources as well. Okay, so the next part then adds to the knowledge graph representation. So now that we have these models running in the cloud and we have all of this information figured out and centralized and located, we need to be able to run them on the edge itself. So how do we do that? In the edge part, we have the model part where we have the data scientists creating the models and the operational engineers sort of connecting those pipelines. But when we're running it, instead of just running it on the cloud, we want to be able to run them on the devices available on the edge, which could be something as big as like a server rack or something as small as a Raspberry Pi also. So the way we add that, or the way we connect it, is we use a knowledge graph, and the device experts, they're the more knowledgeable ones on how to onboard that particular device onto the knowledge graph to say these are the capabilities, these are the resources available for this particular device. And the field engineer then can pick not only the model that he needs to run, but also the particular device by using that mapping and then matching up that mapping with all the metadata, and then actually run the particular application on that particular device. And now anytime that model or the device gets updated, we have this whole chain of connected components that can push down the most up-to-date model version when the connectivity is restored or when there's a bandwidth information available, and then run those models on that device. So here's a knowledge graph example where at the top we have the capabilities, at the bottom we have the actual data. The right-hand side is the applications or the particular models, and the left is the final actual devices. So this is just an example of a filled out sort of mapping that would connect both of them. So in this case, when the data scientist onboarded the pipe corrosion detection, they required some certain capabilities that doesn't have to be GPU, CPU will work fine. And then they required some type of actually specified image data, that this has to be the resolution, height, width, FPS, things like that. And then the device, when it was onboarded, the data scientist or the field engineer created instances of those devices and then gave them the metadata capabilities as well. So when one of these users tries to run this application, this automatic mapping is created so that we can know exactly where this application is going to run and manage that over time as well. Okay, so now Teresa will talk about what we've taken, how to actually take it and then go and run it on your own governance environments and applications.
Thank you, Ish. So we talked about a story and we motivated a particular use case around oil and gas, how we needed to manage these models at scale, right? It was no longer just about model creation, but it was really the operationalization and automation of making sure the models stayed correct, stayed accurate, so when a decision was made, that we'd had confidence in it. And then Ish is showing how that would work for scaling, right? So there's different roles, this DevOps type approach, that when the data scientist is creating the model, that they're thinking about the longevity, how their models, he was talking about a use case where there's surveillance analytics, there's a asset engineer, kind of like continuous integration, right? So each different persona is creating a model that they know, but it's something that is discoverable and reusable by different parts of the enterprises and different parts of the business. And then ultimately being able to deploy this, not just in the cloud, but at the edge, and having this all connected in this knowledge graph. So you would need that to be able to dynamically notify if there's something that didn't work and needs to be fixed, right? So this is what you need to do this at scale and at speed. And so what this unlocks is skills, right? So finding even one really good data scientist is really hard. So how do you scale that and make the models reusable? Scale to actually manage the different parts of deployment, like in the IoT use case, or maybe in the finance and risk use case to make sure that you're running the right models. And then finally, governance, right? So how does this look like? So the skills, again, what we show here is a ability to actually create an application catalog, right? We talked yesterday in one of my talks around data and models being thought of like products. So just like an app store, imagine you have a model store. And since it's so hard to get not just a data scientist, but a data scientist with domain experience, now imagine having this model catalog like you do an app catalog. And in that catalog, you have all the models that have been created, that have been proven out and validated, right? So that's the first step that enables scales. If I can, instead of creating my own, discover one, and then maybe run it in the champion challenger fashion that Ish was showing, this will have a way to monetize whoever models is best. I can track that model is best and use that model for prediction or for action, and then maybe do some chargeback based off of that. Scale, right? So the ability to now, once something has been validated, instead of manually looking, that must be like the most boring job if you had to manually look at your models to see if they were still accurate. And in fact, even as a, someone told me a joke about being a developer. It's like trying to be a detective in a murder case where you are the murderer, right? Wouldn't it be the same thing like as a data scientist. So being able to now at scale have automation monitor your models and to be able to try to see if the model is drifting, to be able to do something to retrain it. This is what we've been doing with code for a long time, but now we need automation to do that with models. And then finally, governance, right? So again, it's not POCs that we're talking about. We're talking about operations, where Jürgen was saying if you make a decision to take down the power plant, to turn it off, that's a big impact. So part of this is to add the right governance mechanisms to make sure that the business approvers have approved about this. And if you think about more ecosystem type story, right? So in an oil and gas example, think about all the people who are at that site, right? So you might have the person who owns the well, like a Shell or a BP. You might have all the field services, like a Schlumberger or an ABB. And then you might have maybe the power utility company, right? So you need this ecosystem of different providers to make sure that the well is operating properly. And you probably see this ecosystem story in your business, right? So finance, you would have different partners that you're working, health. So this ecosystem story is very common, and the data that you need is probably the same, right? The same data about the production of the well in our use case. So having a way that allows the same data to feed off a number of models that will then detect and do some sort of action, that needs a governance story that starts within the org, but needs to be thought about how do we govern this across the economy so that every part in that story, the BP, the Shell, the Halliburton, the ABB, have all agreed upon this is the right models to make sure that this well is operating properly, and that if we detect something, we're taking the right action. So this just talks about a model story, but think about this overall journey, right? We have everything from starting, there's two parts of the story. There's the discovery zone, and we're not actually doing too much with the discovery zone. There's still a lot of hard work for data scientists to develop the models, for engineers who know about the physics of the system to develop the models, for the financial services analysts to create models. So it's not fixing that part. But for the second part of the journey around the operationalization, so now that you have these models, how do I scale them? How do I enable other people in my business and even in my partner economy to use these models in a way that is right and that's going to make the bigger outcome? How do I do that? So taking that data science model and then going into this DevOps approach, right? This ability to make sure I'm doing continuous integration for my models. A way that makes sure that governance and auditing, that I'm using the right models, and then decisions that are made automatically have all been approved by the business. And then finally, that cross ecosystem. So maybe one way that you can see people competing in the future is on the data and the models. So maybe I'm going to be an expert. Let's say I'm an engine manufacturer. So maybe I make engines today. And so using my engine data, I'm going to create an initial set of models using my engineering know-how and the data that I have. But let's say I'm going to monetize these models. I'm going to sell it to all sorts of other engines, and then if I'm going to sell them on outcome, right? And then I'm going to get access to their data and thus better improve my models. So maybe in the future, I'm not going to be just an engine manufacturer. I'm going to be this completely data-driven and model-driven business where I'm this engine outcome type analysis. So hopefully we've given you some ideas of things that you can do. This is something that we've done and we've seen at scale in oil and gas, but in other businesses as well. And we will have these slides online, but we also have two very detailed write-ups. One that is talking about model management, just the workflow and thinking about it in a DevOps approach, mainly in the cloud or in your platform. And we just have a new one, this Find Your Edge, that takes that same governance approach that still has to happen centrally, right? Someone still has to create the models, bless the models somewhere centrally. But then at the end, and especially in an IoT setting, you would deploy those models to the edge. So instead of bringing the data to the cloud, right, you're going to bring the analytics to the data. So I think that's what we had to say. Do you have any questions? I think he's going to get a...
question is around what does the deployment environment look like? I mean, a reason I ask this is, a lot of times different data scientists would have their preferred choice of packages that they would want to use. So, how do you kind of give that variety in the environment where it is getting deployed?
So one of the things, we see this, every data scientist actually has the weirdest tools and the weirdest libraries. That's Jürgen. It's always he goes to a conference like this and he comes back and suddenly he wants to play with like PyTorch or something really weird, right? And it changes week by week. So what we have is this architecture that you see here. It's really meant to be an ecosystem approach. So the job server runtimes, we have R, Python, SAS. It's really meant to scale. So when there's a new type of runtime, we'll have a new type of job server there. And so one of the things that we would see, like the example that Ish showed in the risk models, it was a combination of SAS models that have already been developed that are doing risk models. And then there was a separate set of R models that were actually scoring the effectiveness of those SAS models. So it's a combination and a mix that we really designed this for.
Right. So much of the process that you explained, in terms of model creation and model management, did you actually use a workflow or platform which will kind of stitch all these things together?
So it's API driven. So part of it is most companies have SDLC for software development, right? So you already have pipelines. In many financial services companies, they already have some sort of governance for models in particular, but you certainly have data governance already. So part of why we were API driven was we see that you would embed some of this model metadata and model governance into those existing workflows. But the UI that you see was one that we've created, and we have a productized version of the UI that will have a model-specific workflow if you wanted.
Yeah. So you have a slide where you're trying to build a model pipeline using two existing models and then using the third one. Okay. So when you're doing model versioning, how does that actually work? So the models that you're using, my version would have been changed. So how do you actually know what version to use there? I think not this slide. I mean, I think
in the demo, right? In
yeah.
the demo we had. So part of the whole reason about having this framework is versioning, right? So just like with code, like you have a way that when someone updates code, there's a way to track and change, and you don't want it naturally to automatically do things. So part of it's just notification. So when Jürgen, let's say I have a system that's working and then I notice that it's no longer healthy, it's no longer accurate. So then Jürgen would get an automated, through the framework, he would get it either through the API that we have, it might send him an email that says the model is no longer accurate and here's all the runtime details about why it's not accurate. And he can look at it and maybe the system automatically undeploys the model so it's not taking action on that inaccurate model, and then Jürgen would fix it. So the fixing it could take a while, but when he does fix it, he would update the new version into the tool, and that kicks off the, maybe it's a business validation that I do. I look at it, I say, yeah, let's go with this one. And then Ish, through the framework, he might get something that generates a JIRA ticket. And so he would say like, oh, there's a new version of the model. It's been validated by the business owner, Teresa. And so now Ish can go ahead and roll it out to all the places he needs to roll it out to.
So you're saying that the pipeline, you're basically pinning down the version of the model to the pipeline, right?
It's all tracked together, just like you would usage, right?
Yeah, thanks.
Hi, thanks for the presentation. In the demo, you grayed out the ETL bit, I noticed. And I know the talk isn't for the ETL, but I wonder if you could just say a few words about what would happen if a data scientist engineered some new data features as part of the model build. How would that kind of flow through the framework?
I think sometimes you can have an extra model step. So in particular with edge use cases, having the connectors that translate from, let's say, even serial interfaces into a data type. It's just another step. So just like he has a resource for other parts of our pipeline, you could have one around that data interface. I think Jürgen.
So the main reason what we wanted to achieve was model parallelism on the one side, and data parallelism on the other side. The point is, to do both at the same step is extremely complex. And the other thing is, I wanted to educate my data scientists, because a lot of them have very bad habits that 80% of the R code or Python code they write is data manipulation and has nothing to do with modeling. And when I speak with the data engineers in our architecture group, they tell me that has to be done in a data parallel world. And this is some of the, say, performance issues you create in machine learning if you do that 1,000 times in the model and you repeat that over and over. So that's why we're very strict in the coding environment to say as much data manipulation we want to do upfront on a Spark cluster instead of in a model cluster. So that's the reason why we do. We are not fully excluding it, because sometimes you have highly specific manipulations you do. That's okay. But you not do 80% of your code there.
Okay. Well, thank you for your attention. And we are hiring if any of this looks interesting.